So today we're going to at least start section 2.1 over mathematical systems. And then we're going to look at two different kinds of proof techniques. The first one being direct proof, which is the most common type, and then counterexamples, which is a way to show that theorems are false or that things are not theorems. But before we get to proving things, we need to first talk about mathematical systems and what that means. Switch colors here. So a mathematical system consists of things like axioms, definitions, and undefined terms. And then we'll talk about each of these in turn so that we can get a better understanding of what they mean. Though I think it's likely that you've run across all of these in your mathematical education. Let's just start with axioms. These are things that you're going to assume are true. So we're not going to try to prove our axioms. We're just going to assume they're true. And I'm going to pick some examples from geometry for this first discussion, since we probably all have a good memory of these kinds of axioms and definitions from geometry. And one of the axioms that you probably learned back in high school is that there is exactly one line between any 2 points. And this is something that you assume to be true. Okay, and this is just one example of an axiom. You might remember others. We'll talk about, I think, at least one more example from geometry in a few minutes. So next up for discussion are definitions. And this is a way to create new concepts from concepts that you already know. So for example, sticking with geometry, a triangle is a right triangle. And here I'm defining the word right triangle, or the pair of words. In this case, a triangle is a right triangle if one of its angles measures 90 degrees. Or if we were working in radians, we might say pi over 2. So here we're combining the idea of a triangle, so a polygon with 3 sides, with the idea of angle measures, in this case, the specific measure of 90 degrees. And you probably remember lots of important properties of right triangles, like the Pythagorean theorem and other things. Next up, after definitions, are undefined terms. And this one is a little bit harder, just a little bit, because, well, we're deliberately leaving things unspecified or undefined. And these are things that are implicitly defined by the axioms. Like in geometry, you never have an axiom for what a point actually is or what a line actually is. The axioms just define implicitly what those are based off of their properties. And in basic set theory, like we talked about, our undefined term was actually a set. We didn't actually define what a set was. Okay, so these three concepts, axioms, definitions, and undefined terms, these make up a mathematical system. But what we usually do in math is use these basic ideas, axioms, definitions, and undefined terms, and we want to prove things about them. We want to figure out what their properties are. And the way that we do that is by creating things called theorems. So these are propositions, or a theorem is a proposition that has been proved to be true using properties of logic, along with the axioms, definitions, and undefined terms of your mathematical system. So an example from geometry of a theorem is this one. If two sides of a triangle are equal, then the angles opposite the sides are also equal. So this is something that involves the concept of a triangle and then lengths of sides, the idea of things being equal, and then also angles. So it combines all of those ideas and puts them into a proposition, a conditional proposition. And these kinds of statements are the ones that we're interested in usually in math. And then there's two types of theorems. So these are also theorems, but sometimes they get special names. You might have seen the word lemma or the word corollary. And lemmas are usually simple theorems that are useful to prove other theorems. But by themselves, they're usually simple and maybe not very important if you just look at the lemma. So usually simple and maybe uninteresting. Maybe it doesn't say anything that's very important. And that gives the name lemma. They are types of theorems, though. There's still propositions that have been proven to be true. And the other type of theorem that you'll often see is called a corollary. And these are theorems that are easy to prove if you know another theorem. Okay, so are there any questions at this point over any of these concepts before we move on to a few more examples?
What is that part in parentheses of lemmas?
It says usually simple and uninteresting. So a lemma by itself is usually not very important. So simple and maybe uninteresting, but useful. They're used for other things. Okay, so next I want to look at just a few more examples of what these things are before we get to actually making our own proofs a little bit further on. So from geometry, we can think of other axioms. The one that I'm about to write is usually called the parallel postulate. It says, given a line and a point not on the line, we're able to find another line, or there is another line that's parallel to the original one, and through the point. So in pictures, here's the idea. If I give you a line like this one and another point somewhere off of the line, then this axiom tells us that we're able to find or draw another line through the point parallel to the given line. So something like this dotted line. Okay, so far we've looked at lots of geometrical examples. Let's also think a bit about the real numbers, some axioms of the real numbers. Maybe a couple. One of the axioms of the real numbers tells us that we can multiply things in any order that we like, called the commutative law. And here's what it says in precise words. For any real numbers, x and y, x times y equals y times x. And you should recognize the construction of this proposition as a nested quantifier. So we're talking about for any real numbers, x and y. So this is something like for all x and for all y, xy equals yx. So whenever you see an axiom or a theorem or something like that, it's important to think about what kind of logical construction you're looking at and how it compares to what you know from what we've learned in the class so far. Here's another example. This axiom has to do with the number 0. It says there is a real number, and we usually use the symbol 0. Where x plus 0 is equal to x. So I can add 0 to any number and it doesn't change the original. And again, this one is a universally quantified statement, but this one is only a single universal quantifier, since we only have a single number x. Any questions before I go down a little bit about these kinds of axioms? Okay, so let's look at a few more definitions. And I'm not going to write out the whole definitions here because, well, I suspect you already know them. I'm just going to remind you of the kinds of things that we define in mathematical systems. So in geometry, you might want to define what a triangle is. Or a circle, or a rectangle, and so on. And you might have some definitions involving angles, like this one, that says two angles are supplementary. If their measures sum to 180 degrees. And you probably know lots more definitions from geometry if you took a second to think about it. You know all sorts of shapes, squares, rhombuses, trapezoids, octagons. Each of those words has its own definition. So let's go over to the real numbers again and look at some definitions for those. Again, I'm not going to write out the whole technical definitions, but you might have something where you might want to define the positive numbers. These are the numbers larger than 0. And the negative numbers, the numbers less than 0. And there are other concepts like the absolute value. And we could just keep on going on this list if we wanted. So remember, the absolute value of a number depends, oops, let's try that again. Bad handwriting. The absolute value of a number depends on the value of x, whether it's greater than or equal to 0 or less than 0. And we often use this kind of piecewise notation when we have different cases of things. So the absolute value of x is equal to just the number x if you have something greater than or equal to 0. But if you have something less than 0, you have to put an extra minus sign on it so that it becomes positive. So any questions about what definitions are?
Professor, can you scroll back up on for the right side a bit?
Are you asking about the axioms?
Yeah, right there. That's good.
Okay.
Good now.
Okay. Okay, so we've looked at lots more examples of axioms and definitions. Let's talk about a few more kinds of theorems or what they could possibly look like. And in particular, I want to talk about corollaries and lemmas. Okay. Some examples. So we already looked at an example of what a theorem might look like. Here's an example of a corollary. And this one is easily proven if we know the theorem that we learned on the first page. Well, you probably already knew it. It says if a triangle is equilateral, meaning all of its sides are equal, then the triangle is also equiangular, meaning all of its angles are the same. So if you wanted, you could think of how to use the theorem from the last page to prove this one, if you wanted. We're not going to go through that, though, or at least not today. This theorem, this one here, is a little bit more complicated than the kinds of things we're going to get started with. So back over to the real numbers, this right-hand column. You could have a theorem that tells you what happens when you multiply a number by 0. So for all real numbers x, x times 0 is equal to 0. This is something that you could prove using the axioms of the real numbers and logic. And here's an example of a lemma that you might have in the real numbers. This one says if n is a positive integer, then n minus 1 is a positive integer. Or n minus 1 is 0. Okay, so like I said, this is called a lemma because by itself, it's really not very interesting. It's not even as interesting as this corollary about triangles. This just tells us what happens when we count down integers. So if you count down one integer in the positive integers. Are there any questions about what theorems look like? Or maybe I should point out that this one includes an or in it. So it's a conditional statement, an if then, and it says that one of these two things is true, or at least one. Okay, so now that we have, I think, a pretty good idea of what we're talking about, let's try our hand at actually proving things using direct proofs. And to get started, we're going to talk about statements like this. These are conditional propositions. You've probably seen lots of if-then statements in your other math classes. And I think this is probably the most common kind of theorem involving a universal quantifier, a for all, and this conditional. And in order to prove that this is true, and maybe I should spend a second talking about this. So this notation x1 up through xn tells us that we could have any number of things that we're talking about. So in the examples, we had one thing or maybe two things that we were talking about in our theorem, but you could have quite a few more in certain cases. So that's why I wrote it this way. And we're plugging these values, whatever they are, into our propositional functions over here on the right. And in order to prove that this universally quantified statement is true, you have to show that the conditional proposition, the right side, is true no matter what values you plug in. So that's what we have to show. I'll just write that down. So we have to show that this conditional proposition is always true no matter what values of x that we plug in. But there's an important thing that we have to remember about conditional statements, because remember, if the hypothesis, the first part, is false, then the overall conditional statement is what we called vacuously true. So that means if the hypothesis is false, we don't actually have to worry about anything on the right side, because it's going to be true no matter what. So for a direct proof with a conditional proposition, we actually only have to consider what happens when the hypothesis is true, when p of x1 through xn is true. And then we're going to use our tools, in this case, axioms, definitions, maybe other theorems that have already been proven. And then we're going to use our rules of logic as well. So we might need to use arguments and just raw logic to show that the conclusion q of x1 through xn is also a true statement. Okay, so this is in a nutshell what we're going to do, or at least the logic of what we're going to do. The next step is, of course, to actually try it out, to try to come up with our own proof for a theorem. Okay, so for our first theorem, we're going to keep the ideas nice and simple. We're going to talk about even and odd integers, which should be familiar to everyone. So remember, even numbers are multiples of 2, and odd numbers are everything else. But in a more precise definition, we're going to think about them like this. An integer n is even if there exists another integer k such that n is equal to 2k. So this is just a more precise mathematical way of saying that our integer is even if it's a multiple of 2. And the odd integers are the other ones. An integer is odd if there exists an integer k such that n is equal to 2k plus 1. So it's not divisible by 2. It's a multiple of 2, and then you've changed it. You've added 1. Any questions over the definitions? Or maybe we should check that we actually have a good grasp of these definitions by just thinking about some numbers that we know and then putting them in terms of the definitions. For example, 2 is an even number, of course, and making it match the definition, it's even because 2 is equal to 2 times 1. So 1 plays the role of the integer k in the definition. What about the number 6? Is this even?
Yes.
Right, of course. And 6 is equal to 2 times what integer?
3.
3, good. Right, and this also works for negative integers, like -8. This one is 2 times -4. And it works for even large integers, like 1024 is equal to 2 times 512. Okay, so what about the odd integers? 1 is equal to 2 times 0 plus 1. What about 3? How does it work? 2 times what plus 1?
1.
Good. Yeah, and then 5 would be 2 times 2 plus 1. And we could also think about negative numbers, like -41 is 2 times 22. Or excuse me, 2 times 21 plus 1. And a minus sign there. I've been saying 2 too many times. Got a little twisted there. Okay. So those are the definitions, and this is how the precise mathematical definitions match up with our intuitive understanding that you guys have developed, over your experiences in school. Now let's get to our theorem that we're going to prove. This is what we're going to do. We're going to give a direct proof of the following statement. For all integers m and n, if m is odd and n is even, then m plus n is odd. Okay, so this is our first proof, and that means I need to give quite a bit of explanation along the way. I'm going to divide my paper into 2 columns so that we can have some comments. I'll put the proof over here and my comments over here on the right. The first thing to do if you're going to write a proof is to let the person who's reading, let the person know that you're actually going to write a proof. So start by writing the word proof. And when I'm writing this by hand, I usually use a colon like this. Different books have different formats, but this is a good one to get started. It tells the reader what you're going to be doing, and the reader could be you in a week, and you're reading back on your notes, trying to figure out what you were talking about. So it's important that you make everything nice and readable and understandable. And the next thing that you'll want to do after writing proof is to write everything that you're going to assume and everything that you need to show. So this is my first bullet point, and then write what you're going to assume. Maybe I'll fill this in. In this particular case, we're going to assume that m and n are integers, of course, and also that m is odd and n is even. So write it out. We assume that m is an odd integer, and n is an even integer. Another thing to point out before I get any further is that you should always use complete sentences whenever you're writing a proof. So a proof should never look like scratch work that you might write on an exam or on your homework. It should look a little bit more like an essay, almost. Okay, so after you've done this, tell the reader what you're going to do. Write what you are going to actually show. So in this case, we need to show this part of the theorem, that m plus n is going to be odd. Okay, so this kind of gives us an outline of what's going to happen. It tells us where we're starting, what we're assuming, and it also tells us our ending point. And our goal in the proof is to make a connection between the starting place and the ending point using definitions, axioms, and our logic tools. So in order to do that, we have to make sure we understand what all of the definitions mean. So next, you'll want to work through those. In this case, we have an odd integer and an even integer. And going back to the definition, we know that means something very specific. Since m is odd, there's another integer, let's call it k1, such that m is equal to 2 times k1 plus n. That's what it means to be odd. We also have a very specific definition for even integers. So since n is even, there is another integer, let's call it k2, such that n is equal to 2 times k2. And it's important that we use different integers from our definitions. So I'm using k1 for m and k2 for n, because it's definitely possible that these are different. So for example, if m was equal to 1, k1 would be 0. And if n was equal to 6, k2 would be equal to 3. So we have to make that distinction here in our proof. Okay, so we're kind of working through our checklist here. We've used our definitions for m and n. Now comes the harder part. We have to use logic and arguments to connect these ideas to the conclusion. So we actually have to show now that m plus 1 is really odd. Okay. So what we need to do is add our two numbers together. Since we're talking about m plus n, well, we have to actually add them. And now's where we have to use our definitions. So m was equal to 2k1 plus 1. Let's substitute that in. N was equal to 2k2. Let's substitute that in as well. So we're taking the conclusion that we want. We want to look at m plus 1, or sorry, m plus n, and we're connecting it back with our assumptions about odd and even integers. And now we have to show that this is an odd number. And remember, in order for a number to be odd, we have to write it as 2 times an integer plus 1. In this case, we're going to have to do a little bit of cleaning. We need to collect the 2k1 and the 2k2 together. and leave the +1 on the end, now both of these terms share a factor of 2. So let's factor it out. Two times k1 plus k2. And that's exactly what we were looking for. M plus n is equal to 2 times this integer plus 1. So this means we're done. We just have to write a concluding sentence. So you could say something like, since m plus n is equal to 2 times k1 plus k2 plus 1, and we know that this is an integer, k1 plus k2 is an integer, we now know that m plus n is odd. And often in math, it's customary to end a proof with a symbol like this one. So this is a square. Some people like to use a different symbol, but this is the one that I like. So that's what we're going to use. And this just marks the end of the proof. Okay, are there any questions over that proof and how we wrote it?
Is that what every single question is going to look like? Is look like this lengthwise?
Lengthwise, yeah, I think so. This is probably a pretty typical length. I'm not using even the full width of my paper, so it looks a bit longer than it actually is. And I've included a lot more detail in my explanation than your textbook might or you might. But yeah, I think this is about the same length as most of the proofs that you'll do. So a proof is kind of like a mini essay or maybe a short answer in a different class. And proofs to me are really the exciting part about math, because there's a little bit of creativity involved in trying to connect what you're assuming to what you're trying to conclude. Because there's many ways that you could do it, and you have to come up with that way on your own. So it's a bit of a challenge. Any other questions? Okay, so this is an example of a proof where we're looking at a universal quantifier with a conditional statement. There are, of course, many other kinds of statements. So instead of having a conditional here, you might just have a single statement, a single proposition instead of an if P then Q kind of proposition. Maybe you just have a P. And your proof in that case would look a little bit different. And we're going to be looking at many kinds of examples, many examples of proofs over the next few lessons. Let's see. So the next thing I want to talk about in this section is what's called a counter example. And this is a method to disprove a universally quantified statement. So it's kind of the opposite of what we just talked about. And in order to show that this is false for all x p of x, we have to only show, or we only have to show, that p of x is false once. So we need to find the value of x where p of x is false. And it's important to remember that 1 is enough. If you find one place where it's false, you can stop. And this example is what we're going to call a counterexample. So the counter means that you're using it to counter a proposition to show that it's false. So we could use a counterexample to prove or possibly disprove the following statement, or a counterexample would be for disproving. A proof would look more like what we just finished. So this example says prove or disprove the following statement for all n in the positive integers, 2 to the n power plus 1 is prime. So first of all, when we're looking at a proposition like this, is we have to decide whether it's true or false, or we have to get an intuition about whether it's true or false. What do you think? If I plug in any integer, any positive integer in the exponent, am I always going to get a prime number out of this expression?
No.
No. The answer is definitely no. This is false. So if we want to demonstrate that it actually is false, we need to find a counter example. So that's what we're going to do. Oops, false. We need to find a number, an actual number that we can plug in for n. Or more specifically, an integer. And we need to find an example where this is not prime. That's where it's false. And again, this is where a little bit of guesswork or creativity can come in, because there's not really a method to find this number. We just have to come up with it. And one of the easiest ways is just to start plugging in positive integers. Maybe one of you already knows the answer, but let's say I didn't really have any idea how to get started. I could just start with the smallest positive number and see what happens. Maybe I can plug in n plus 1, or sorry, plug in n equals 1. into the expression. So what is this? 2 to the first power plus 1.
3.
That's 3. Is 3 prime?
Yes.
Yeah, so this isn't what we're looking for. That one won't work. What about n equals 2? So 2 squared plus 1. What is that number?
5.
5. Good. Is 5 prime?
Yeah.
Yes.
Yeah, so that one doesn't work either. We have to keep on going. Let's try n equals 3. What is 2 cubed plus 1?
9.
It's 9. Is 9 prime?
No.
No. 9 is equal to 3 times 3, of course. So that one will work. N equals 3 is our counterexample to the proposition. And once you find the single counterexample, you're finished. We already know it's false. Any questions over what we did there?
What is the symbol above 2?
Which one? Which 2? This one? This one? That one?
Oh, it's an N. I got it.
Yeah, so this is the integer.
The one under that, actually.
Yeah.
Yeah, that's an N, right?
It is. Yeah, it's the letter N. These exponents can get a little small and hard to read. Okay, so that actually wraps up the section. We were actually able to make through it today. So I guess the first thing to remind you guys is that I will be posting the homework for this section today, and it'll be due, I guess, a week from today, Monday next week. So make sure you guys look at that and work on it. And since we do have some time left over, I can see if you guys have questions over your current homework. So are there any questions?